Section 3.7 is called efficiency of a machine. So when we're converting energy from one form to another so that we can get power out to do some type of work, there are always going to be losses. No system or no machine is 100% effective in converting energy from one form to the other. Now, some are much better at doing this than others. And what we want to be able to do is we want to look at that as a qualifying characteristic of a particular system, a particular type of machine, and look at that as something that might make us select this over another, so forth and so on. And so Section 3.7 is concerned with that. So there's a fundamental equation that we look at when we talk about efficiency of a machine, and it is given as equation 3.6, and 3.6 says the efficiency is equal to the power that we put into a machine or a system divided into the output power. So we have a certain amount of input power, and it's always going to be larger than the output. There are going to be losses from the input to the output, and then we just make a simple comparison of output power to input power. Then we want to put it in terms of percentage, so we multiply it by 100, and this gives us the efficiency of a machine. Now, this of course is in watts, and this is in watts, and this is a number just giving us a percentage. Now, he goes on to tell us that efficiencies are very low when you're talking about thermal energy converted to mechanical energy. Think about, burning coal to turn, to convert to steam, the steam channeled through a turbine, the turbine connected to a generator, and, electricity coming out of that. Each one of those individual systems has losses involved in it. And so those thermal to mechanical transitions, ultimately mechanical to electrical, they are, he says, in the ballpark of 25 to 40%. Now, when you think about that, at first you might say, well, that's not too bad. But if your efficiency is 25%, that means you're losing 75% of the energy that you put into it. Internal combustion engines are automobile engines that take the chemical energy contained in a gallon of gas and convert that to mechanical energy. Those are in the ballpark of 15 to 30% efficiency. 15 to 30% efficient. And the thing that I like to come back to, especially since this is where we are, right, is look at the efficiency of electric motors. Electric motors have efficiencies from 75% to 98% efficiency. And we'll take some little side trips later in this class, and we'll look at specifics of electric vehicles. And at some point, when you compare an internal combustion engine to an electric motor, and you look at the differences in the efficiencies, at some point, you will see that someday, when all things come together and the stars align, and we're closer to that every day, we will see that at some point, we're going to see electric vehicles become more and more a part of our life. And we're always seeing all car manufacturers make electric vehicles. Some of them are being very successful, like Tesla. And in other parts of the world, they're much more prevalent than they are here. But we're going that way, and we'll look at some of the particulars of that going forward. We have a problem that we can look at and actually do an efficiency calculation. And that problem says, let's say that we have a 150 kilowatt motor and it's 92% efficient. What are the losses? Okay, well, I can tell you, the losses are going to be 8%, right? You lost 8% of what was put into it. But a couple of things here. As we look at this equation for efficiency, I want you to get this and make sure that you understand this. Whenever a motor is described to you and it says it's 150 kilowatts, that is the output power of that motor. Okay, if that is on the nameplate of that motor, then that is the output available at the motor shaft to do work, as we described it earlier. So when you work a problem like this and you're trying to figure out, you know, which goes where in this equation, this is given as the power out. So we have a 150 kilowatt output motor. The power in, we don't know. But what we are told, and I'm going to take this out of this in terms of it being, you know, efficiency. I think it works better here. We'll get rid of that. But what we know is it's 92% efficient. So if I want to know what the input power is, and that's what he's asking, you know, ultimately in here by saying what are the losses of the machine. Well, if I want to know what the power in at 92% was, then I take 150 kilowatts, divide it by 0.92, and I end up with 163 kilowatts. So I put 163 kilowatts worth of power in to get 150 kilowatts of power out. I put 163 kilowatts of electrical energy in, and I got 150 kilowatts power out from that energy input. Okay, yeah, just looking at it in that regard. Then the question is, what are the losses? Well, the losses are 163 kilowatts minus 150 kilowatts, which is 13 kilowatts, which are lost. And we will go through in later chapters, and we will look specifically where those losses occur. Now, let me back up just a minute here. And you know, I'm guilty of this, and you know, I know we want to be careful with this, you know, and I'm sort of using energy and power together in this, and I don't really mean to do that. You know, we've got a formal definition of what power is, right? It's the rate of doing work. You know, these machines convert energy from one form to another to create power. The power is what we describe as being able to do the work that a force over a distance, or however, when we're talking about power of a motor, you know, we have a formula for that. Okay, let's stop this one, and we'll get ready for some specifics of this operation of motors.